Hi. So this is a recording of the class that I'm going to be giving on September 22nd, 2021. Let me write that down. Fans going here because the computer is getting hot. Okay. All right. So last class, we looked at the kinetic molecular theory. Or just the kinetic theory. And we showed that the pressure volume product, where if you remember this brackets under capital KE, this thing here, is the kinetic energy, average, I should say, kinetic energy of 1 mole of molecules. Okay, and so we sort of ended with this, and then I said there were 2 ways that you could proceed. You could assume that the average kinetic energy as a postulate is 3/2 RT. That's done in many books, but I kind of prefer to say, well, and if you set PV equals nRT, then you set these 2 things together. You can actually out that the temperature is related to the average kinetic energy because you have 2/3 N cancel, and your kinetic energy equals 3/2 RT. And this is kind of where I ended. I said a few words about it last time, but this was the main conclusion that I make. And I called this a magnificent conclusion. Now, why do I think it's so magnificent? Okay, I'm going to write that it's magnificent. All right, so a geek like me thinks this is really a great conclusion because it relates a microscopic property. So the kinetic energy of molecules, that's the motion energy of molecules. So I say this is a microscopic property to a very macroscopic property, which is the temperature. Okay, you never have the temperature of 1 molecule or 2 molecules. Temperature is something that can only be measured for a large sample of molecules. Okay, macroscopic property. So that's the first reason that makes this a magnificent conclusion. Another one that is really very great is that it tells you that temperature is a measure of the average kinetic energy of particles in a sample, okay, or molecules, whatever they are. They could be atoms, they could be molecules. So we get a really good handle on what it means for a sample to, say, have a higher temperature. It means molecules are moving faster because you can't change the molar mass, right? And kinetic energy is 1/2 mv squared. So the only thing that can change if you have a sample of molecules and you're increasing the temperature, it's going to increase the kinetic energy. It can't increase mass. It's going to increase the speed. Okay. So this gives us a great conclusion that temperature really is a measure of the average kinetic energy of molecules. But it also shows, well, I was going to say it satisfies our intuition. Which is that as you increase the temperature, that leads to an increase in the speeds of molecules. you heat them up and they move faster and faster, So in that sense, it's really a very good. It shows that the average kinetic energy of molecules depends only on depends only on temperature. Hold on a minute, my eraser is not working right because I made a really small eraser. But okay. Oops, no, it's not good. So it shows that average kinetic energy depends only on T, right? Not on molar mass. That's the symbol I use for molar mass. Not on whatever the volume happens to be, and not on the pressure, unless you have temperature. Okay, but it really, if you know what the temperature is, you know what the kinetic energy is. It's related only to temperature. Okay, so I'll say unless changing these changes the temperature. Would like to take this now. Yeah, right. Remember, we had two equations, right? I kept pointing out that there were two kind of sister equations. So remember, we had this PV is 1/3 N times Avogadro's number times the mass times the average V squared. And we use this one already. That's how we got the kinetic energy relationship. But we also had another version of this equation, which was simply really to group Avogadro's number times the mass together. And that's the molar mass. Okay. So now if we take this equation, which I've rewritten over here, here it is in the worksheet. And now you equate that to the ideal gas law, right? nRT PV equals, and equate these two. So you have nRT equals 1/3 N. What we're going to do is we're going to solve for this. So instead of getting an equation for the average kinetic energy, we're going to see how does the average speed depend on these various things like temperature and molar mass. And so if you just move the 1/3 over to the other side, well, first cancel the n's, then move the 1/3 on the other top side, it becomes 3 RT, and then divide that by the molar mass. There's your expression for the average squared speed, or the mean squared speed. Okay, but most of the time what we do is we actually take the square root of this. The square root of the average of the speed squared. So this is the average squared speed, or mean squared speed, and this is the root mean square speed. And oftentimes we call it the RMS speed. I don't know why Atkins does this, but it's called C in Atkins. So that's why I'm writing it here. I thought C was the speed of light, but apparently it's also the root mean square speed. And it's the square root of 3 RT divided by the molar mass. So that is this expression for the root mean square speed of a gas sample. And you could see right away that it depends on temperature. So as temperature goes up, average speeds are going to go up. But you can also see that it depends on molar mass. And as molar mass increases, the root mean square speed goes down. The larger the molecules, the heavier they are, the more sluggish they are. You can think about it that way. All right, so if you were going to use this equation to actually calculate the root mean square speed. How would you do it? So, you have a nice formula here, 3 RT over M. But the thing is that R in gas law problems is generally in our class anyway, liter, what the heck, it's not erasing. Well, it really likes that. I keep going over it, but it's pretty funny when it does stuff like this. You just gotta laugh, because otherwise you just cry. Okay, so what was I saying? R, here, I'll just leave it there. We generally will use, for gas law problems, 0.08206 liter atmospheres per mole Kelvin, but not here. It doesn't seem like it is, but it is, and we'll get into that later. But when we do this problem, we use R, has to be in joules per Kelvin. And a joule is a kilogram meter squared per second squared. And so if you take a look at the formula, it's the 3 RT over M, and you know that, R is going to be in joules per mole Kelvin, so it's going to have a kilogram unit in it. And you look at the molar mass there and you say, oh, well, most of the time we use molar masses in grams per mole. But in this type of problem, the molar mass must be in kilograms per mole. Okay, so it says, work out the units of the root mean explicitly. And that's what I'm going to show you here in class. I might ask you to do it yourself. I'm not quite sure how I'm going to handle that, but let's see. So we have the square root. The 3 doesn't have any units. So we're using this formula. So R is going to be joules per mole Kelvin. So that's kilogram meter squared per second squared mole Kelvin. That's your R unit. 3 RT is going to be in Kelvin. And then divided by molar mass is in kilograms per mole. So let's see, moles cancel, kelvins cancel, kilograms cancel, and we end up with the square root of meters squared per second squared, which is meters per second. And that's what the root mean square speed unit will come out to be. And that's perfectly fine because that's a velocity, a speed unit. Okay, so now this problem is asking you to calculate that root mean square speed for an ammonia molecule. It has to give a temperature. Well, the molar mass of ammonia is 17 grams per mole, but we have to use it in kilograms per mole. So you have to move the decimal place over a little bit. So we have 8.314. We already did the units, so I'm not going to show it here. 298 over 0.0170. Take the square root of that. And it comes out to, what do you think it's going to be? It comes out, it's an amazingly huge speed, 661 meters per second. Those molecules are really shooting around there at 298 Kelvin. They're having a good time. Anyway, another thing that's often done is to calculate the ratio of the root mean square speeds of, say, 2 different samples of molecules. So what would the ratio be of a sample of ammonia molecules to the speed of a sample of hydrochloric acid molecules? And the reason I use this is because I used to do a demo in a class. And in the demo, I'd have, I have a nice long skinny tube that's much nicer than the one in the picture. And I would take some cotton and I douse it with concentrated ammonia and concentrated HCl on one side. And what happens when ammonia and HCl come together is you end up with solid ammonium chloride, right? These are both gases. And so what you see is that, you start to see some of the solid. And you'll notice that the ammonia has covered maybe 2/3 of the tube, and the HCl only, because what's happening here is that the molecules are moving this way, and these molecules are moving that way. This is basically diffusion and is proportional to the root mean square speed. So let's take a look at this. This is going to be the square root of 3RT divided by the molar mass of NH3 over the same for the molar mass of HCl. But what happens here, of course, is that everything cancels except for those molar masses. And they're the ratio of those reciprocals. So you end up flipping the bottom fraction and you end up with the molar mass of HCl on top. And I am doing all the color stuff here, right? And the molar mass of NH3 on the bottom. So that's VRMS NH3 over VRMS of HCl. Okay, so you can see that these guys are flipped. So let's finish doing this calculation. So in other words, what I'm saying is you don't have to actually calculate the speed, the root mean square speed of the ammonia molecule or the HCl molecule. All you need to do is take the inverse ratio of their molar masses. So the molar mass of HCl, it's got a chlorine and a hydrogen. Let's just call it 36.5 grams per mole. And the molar mass of the NH3, again, is 17 grams per mole. So the ratio just recopying, is the square root of, so you put the ammonia one on the bottom and the HCl one on the top. Okay, and that comes out to 1.46. So you could see that that the ammonia is faster by a factor of 1.5. So it could move 1.5 times. So maybe this, I drew this maybe a little too, maybe it would be more like over here. But it would certainly, this is a greater distance here than this is. Okay, it's about 1.5 times this distance. So this is more like, 1.5 times. All right, so that's the kind of thing you can calculate. And so that's the case. So diffusion rate is proportional to the root mean square speed. So that's, if you open a bottle of ammonia on one side of the room and you start to smell it on the other side of the room, that ammonia is going to move with a speed that's depends on its molar mass. Which, if you had HCl next to it, you wouldn't smell it as quickly because it would diffuse more slowly. And the same is true of this related process, which is called effusion, which is the movement of gas molecules, but not say across a room, but from through a small opening from a region of higher pressure to a region of lower pressure. So it's just illustrated with this simple picture here. And again, the same is true of effusion rate as diffusion rate. The rate is proportional to the root mean square speed. The relative rate of effusion of gas 1 to gas 2 is the inverse ratio of the square root of their molar masses. So it's exactly the same relationship as the one we just talked about for diffusion. Okay. And here's a little problem. Effusion used to be the method of choice for separating radioactive isotopes. And so basically, we're talking about uranium here. So what they would do is they would take uranium and which is of course a metal, and they'd react it with fluorine. Okay, so they would form UF6, and then they would vaporize the UF6. All right, and then they would pass it through many chambers like the one that I show up there. Well, why would they do that? Well, it's because there are really two major isotopes. There's uranium-235. This is the one they wanted for bombs, right? For so I guess I'm talking about separating radioisotopes for the making of the atomic bomb and other things. So they wanted U-235, but uranium is mostly U-238. So in any sample, you're going to have a whole lot more of the U-238 than a U-235. So you need to enrich the uranium in the 235 isotope. Or how to do that is if you make it into vapor, into UF6 vapor, so then you're going to have U-235 F6 and U-238 F6. And look at this. This one weighs 238 plus 6 times the molar mass of fluorine. This comes out to 352 grams per mole. And this one comes out to 235 plus 6 times 19, which is 349 grams per mole. Not very different. So, but that did not deter the scientists back in the Manhattan Project, because they probably couldn't think of any other way to do it. So this is the molar mass of 235 UF6, and this is the molar mass of 238 UF6. So the relative rates of effusion of 235 UF6 to 238 UF6 is square root of the molar mass of the 238 over the molar mass of the 235 gas, which is the square root of 352 over 349, which is 1.004. So that means that every time these gas molecules effuse through from one chamber to another, there was a 0.4% enrichment with each pass. I'm going to call them a pass, like each chamber. Well, that's not a lot. So what you have to do is this must be done over and over again. So, you know, I might say, okay, it's just going to be a really long thing. You know, it's going to go on and on. Where you start out with a high pressure and you keep going, But that's not quite how it looks. The way they would do it is they would have, let me just make sure, okay, they would have this, so these large red blobs represent the bigger U-238, exaggerated larger size. The U-235 blobs are smaller, and so here would be your membrane, and you would have effusion going in this direction, and this would all be in a flow system, so it'd be flowing continuously, and then this would go into the next chamber, and on and on. Nonetheless, you need a lot of real estate to accomplish a thing like this. And I'm just going to show you this picture. I love this picture. Because look at this place where they did this. So there are so many stages, so many of these chambers that were necessary for enriching the uranium to a sufficient level, that this thing has 4,000 what they call stages. And this guy was a half a mile long, 6 stories high, and covered 43 acres. So, you know, bomb makers needed to come up with a better way. So nowadays, this is done with the use of a centrifuge. But back then, there were no, that was not a technology that anybody had. So that was basically how the enrichment was done for the first atomic bombs. Those are not done it's not done anymore. But there's still a national lab in Oak Ridge, Tennessee, but it doesn't perform this particular function anymore. All right. So I just want to get back to this. Kinetic energy is 3/2 RT again. This is for 1 mole of gas. So for 1 molecule, what you would do is, you know, it would be this divided by Avogadro's number. So it would be 3/2. I'm going to divide the R by Avogadro's number, because this thing here, R over Avogadro's number, is a very important physical constant on its own. This is called the Boltzmann constant. And very, you know, unimaginatively, it's been given the symbol K. Okay, so, and you can calculate what it is. It's 8.314 joules per mole Kelvin divided by 6.02 times 10 to the 23rd. So that's molecules per mole. So moles cancel. And if you do the math here, you end up with 1.3806 times 10 to the minus 23rd joules per Kelvin. Now, technically, it's joules per Kelvin per molecule, but this is generally left out. It's like, well, what is it going to be? If it doesn't say mole, it must be for 1 particle. So you don't see that very often. It's just the Boltzmann constant is 1.3806 times 10 to the negative 23rd joules per Kelvin. I always remember that this is negative 23rd because it's the opposite of what Avogadro's number is. Okay. All right. So we know that a sample, say a mole of gas molecules, that the average kinetic energy is 3/2 RT. This is for 1 mole. And, you know, we know that in that sample that the molecules are not all moving with the same speed. There's an average speed, and we know what the average kinetic energy is from that average speed, but we do not know what their speeds are exactly. But another thing we can sort of figure out is, well, I'd like to talk about the fact that there are 3 directions of the motion of any molecule or molecules in a sample. And we call these directions the X, Y, and Z directions. So if you have a sample of a gas and you have randomly moving gas molecules, so you have a sample of, you know, according to the kinetic theory, randomly moving gas molecules. One question you could ask yourself is, how is the energy of motion in one direction related to the energy of motion in another direction? How is the energy of motion that these molecules have sort of parceled out between the 3 directions of motion? So how would the motion energy So that's the, the kinetic energy that we know the average, we know what it is. But how would it be sort of divided up among the three directions of motion? Well, there's really, unless you have a magnet set up in the room or something that's going to give a prevalence of motion in one direction or the other. For, a magnet wouldn't even do it unless it was a magnified particle, magnetic particle. But if there was just a sample of gas moving randomly, you would expect that the motion energy would be divided up equally. Okay, and as a matter of fact, there is a principle in physics that we call the equipartition principle. And the equipartition principle basically says that if the motion is random, then the energy would be divided up equally. The kinetic energy would be divided equally over the three directions of motion, or we also call this the 3 degrees of freedom of motion. So that is to say that the average kinetic energy, which is 3/2 RT, which would be the sum of the kinetic energy, the average kinetic energy in each of these directions, okay, that these would all be the same. Okay, so that would be, so that's like 3 times the average kinetic energy in the x direction, right? So just continuing with this a little bit. So that would mean that the average kinetic energy in the x direction, which would be the same as in any of the other directions, would be, well, it would be 1/3 of this, which would be 1/2 RT. Okay. And if we did this per molecule, so this is per mole, but per molecule, if you remember, we use the lowercase kinetic energy, and everything we said for 1 per mole would be the same per molecule. So I'm using lowercase now, would be 1/2 R divided by Avogadro's number, which would be the Boltzmann constant. Okay, 1/2 kT. So the point that I'm getting to here, a little convolutedly, is that the kinetic, kT for 1 molecule, or RT, I'll put it in quotes, for 1 mole, has a very important meaning in chemistry. It's really a measure of the energy that is available to molecules by virtue of the fact that the temperature is not 0. Well, that's a very funny way to put it. The energy available to molecules. Let me write that down. Energy available to molecules by virtue of the fact that the temperature is not 0. And we know it can't be 0, or we will know in a little while, because the third law of thermodynamics declares that absolute 0 is not attainable. So, so the energy available to molecules. Okay, so what do we call this energy to sort of express this idea that it's energy because the temperature isn't 0? And it's, it's because this expression here for the energy in each direction, or even the average kinetic energy entirely, it depends on that temperature, on that RT or KT for one molecule. And so we basically call this thermal energy. Atkins also has a funny way of calling it. He calls it loose change energy. Well, okay, so I did mention the third law of thermodynamics, which we cover later on in the semester, says that basically absolute zero is unattainable. You can get very close, but you can't get there. So that means the temperature is never zero. So there is always some thermal energy. Okay. All right. So that means that molecules always have kT, about kT of energy to use to do things. Okay. If you're talking about a mole, it has RT of energy that's available for use. Okay. So let me talk a little bit about how KT and RT show up in equations in chemistry, some of which you've seen already, one in particular that I want to talk about. So, so I'm going to try to give you a little more insight into, I'm actually going to talk about the Arrhenius equation. Okay, so KT and RT show up in many important equations in chemistry. So how, where, what's a good example? Here's one. This K, this is not the same as that K. This is the rate constant. K is equal to A e to the minus EA over RT. There it is, RT, okay? So KT and RT show up in equations. Where they show up, where the RT or KT shows up is in ratios. This is a ratio with a needed energy. Let's review what this Arrhenius equation is all about. So why would you have an RT in this ratio, in this equation? So here, if we just do a simple diagram of a reaction, here is your EA, your activation energy. This is we call the transition state. In going from reactants to products, there's always some kind of, well, most of the time, there's some kind of barrier, right, to go over. Why is there a barrier in the first place? Okay, so why a barrier? Okay, well, in order to get to products, you've got to, shuffle those bonds around. You've got to break bonds, you've got to make bonds. A lot of times you have a distortion of bonds or breaking of bonds before you make ones, right? So if you're going to distort the bonds, you need to get those reactants into the correct position to react. You're going to distort bonds, and this requires energy. Okay, there are also things like you might be breaking up some intermolecular forces with a solvent, let's say. With solvent molecules, if you have hydrogen bonds that are going to be broken, that requires energy, okay? In biology, there are substances that help with these high activation energy processes. Of course, those are called enzymes. They can help find a pathway where you're not needing to do so much distortion or breaking of intermolecular forces. But generally, there is a barrier that you have to go over in a reaction. So you might ask the question, well, where do molecules get the energy from to go over the barrier? So I'm going to answer that here. Molecules get the needed energy, the needed EA, okay, from thermal energy. That's the kinetic energy, their motion energy. Or I say energy of their motion, just due to that, sort of random motion of molecules according to what the temperature is. Okay. So KT or RT, it really tells us how much energy these molecules have. How much thermal energy, this random energy. EA is how much is needed. So there's how much they have and how much is needed. And so this ratio, EA over RT, compares the needed energy. My pen is slipping because the computer is very warm, over the available energy. So that's what this ratio does, is it compares the needed energy to the available energy. And the Arrhenius equation is a mathematical comparison, I would say, of needed energy to available energy. So the rate constant, that's the K I'm talking about here, okay? A e to the minus EA over RT. Okay, so let's think about this ratio, EA over RT. So if the needed energy is much greater than the available energy, that means, that would imply that EA over RT is large. Okay, so we have this exponential. That would be e to the minus of a large number. Okay, well, e to the minus something very big is going to be a small number. Okay, and that's because if you look at the graph, well, here's be a graph of, if I have e to the minus EA over RT versus EA over RT, e to the 0 is 1. And then the graph is a very fast decaying exponential. Okay, so the maximum value of this function is 1. But we're looking at large values of EA over RT. So we're looking down here, right? We're looking over here. Oops. These are large values of EA over RT, okay? And so if we, if we're out here, then we'll have a value of EA over RT that's extremely small. Okay. So we interpret this. This is interpreted. This is the fraction of collisions. Suppose you have a reaction, A plus B goes to C. The fraction of collisions that have the required activation energy. And since so much energy is needed compared to what the thermal energy is, you will actually have a very small fraction. If EA is much greater than RT. Okay, so that's one thing that could happen. So now I'm going to give you the sort of the on the other hand, right? Okay, and on the other hand is if the activation energy is much smaller than RT. Okay, then looking at that ratio again, the needed energy over the available energy is going to be very small. So we'll have e to the minus small number. Okay, if you remember now the graph that I just showed you, as EA over RT increases, this drops from 1. So a small value here of e to the minus EA over RT would be a large value close to 1. So you'll get a value that's near the maximum of 1. Okay. So you would have a fraction of collision complexes with the needed activation energy is near 1 or nearly 100%. Okay. So we can actually take this a step further with the Arrhenius equation. So we know that the rate constant K is equal to A e to the minus EA over RT. And I've been talking about this part, which is the exponential factor. But there's also this part, which is what we often call the frequency factor. For a reaction between two molecules, this would be something like a collision frequency. Okay, so if there's a very high collision frequency, there would be a large rate constant, well, relatively large. It depends also on this other factor, right? And okay, so here's the thing. If the activation energy is much less than the available energy, that means that this exponential factor will be near 1, right? This is e to the minus small, which will be, you know, like over here, it'll be just about near 1, okay? So that would mean then the rate constant, K, would be about A times 1, right? I put 1 in. So that would mean that the rate constant would be determined by the frequency of collision, right? Here, in this case, the K would be determined by the frequency of collisions. And if that's the case, we call this diffusion controlled. We say that's reaction is diffusion controlled because the activation energy is so small that what's keeping the rate down, let's say, is the slow frequency of collision. But generally, these would actually be very fast reactions because, so that was a really bad example, because if the activation energy is low, usually the frequency of collision is very fast. And that would mean that you would generally, these are generally extremely fast because there's no, you know, no significant activation energy. It's very small. On the other hand, if EA is much greater than RT, right, then we have the rate constant is e to the minus a big number, right? And this can approach 0. This is very small. And then we say that the reaction is activation controlled. Okay. All right. What about the effect of temperature? And before I go on drawing all kinds of diagrams, let's just think about the effect of temperature, just to think about what it would be. Okay. So if you have a higher temperature, then you have more of these collisions with the needed activation energy. Okay. So because there's more, there's basically a larger amount of thermal energy. There's more thermal energy. And, there's a greater KT per molecule, so a greater RT, I guess I should say. You have more collisions with the needed activation energy. And so you expect a greater rate constant. Okay. On the other hand, if you have a lower temperature, you'll have fewer collisions with the needed activation energy, and you'll have a slower reaction. Okay, so let's look at this graphically, because this is kind of a cute way of looking at it. So here again, I have my e to the minus EA over RT, just like e to the minus X versus X, e to the minus EA over RT versus EA over RT. And we know it starts at 1 and it drops very rapidly depending on the temperature. Well, anyway, actually, that's not really what I want to say. So we can think about what happens as we change the temperature in this way, okay? If we're going to be increasing the temperature, so we increase the temperature. Since temperature is in the denominator here, right, that means we're really going in this direction. This is increasing the temperature. Is going to a smaller value of EA over RT. And as you do that, so this is increase the temperature, you're increasing that exponential factor. That's getting closer to 1. So as you increase T, so that ratio EA over RT, this is getting bigger, this gets smaller. So you have e to the minus something smaller, which is closer to 1. Okay, so you have an exponential factor that's closer to 1. That's going to mean a faster rate. In other words, a larger K. Okay, larger rate constant. If you decrease the temperature, EA over RT gets larger. So you're decreasing this, so you're increasing this. E to the minus larger is smaller, closer to 0. So you're going to have a smaller K. What are you doing on this diagram? When you decrease T, I'll draw it in black, you're going this way, okay? Because T is in the denominator. As you decrease T, you increase the value of EA over RT. And so you're moving in this direction. Okay. So there's a huge effect of temperature. So if you increase the temperature, you increase the thermal energy. You have a greater number of molecules that have the activation energy to go over a barrier. And and you will have a faster reaction, a greater rate constant. Okay, so what if you are given, so suppose you're given an EA value and asked, is this large or small? You have to know what to compare it to. You need to be able to compare, you need to know what large or small compared to what, okay? So that's really kind of a dumb question. You have to be able to compare it to RT per mole and to KT per molecule. So if you're given an EA value and asked, is this large or small? You have to say, wait a minute, need the temperature. I need to know what is the temperature. Okay, and then I must compare EA to RT. Now, generally, EA is given as joules or kilojoules per mole. So we use this one because this is per mole. So we use the kinetic energy average per mole. It's not quite that, it's 3/2 of that, but it's close enough. So let's do a simple calculation here. Let's figure out what is RT at 298 Kelvin. That's room temperature. It's 25 degrees C. Okay, so it's 8.314 joules per mole Kelvin times 290. Okay, so RT at 298 is 2478 joules per mole, or 2.4, let's call it 2.478 kilojoules per mole. Okay, so suppose a reaction has an activation energy of 53 kilojoules. Now I know what to do. Now, if you ask me, is this a large activation energy? I could say, well, yeah, you need 53 kilojoules, but at 298 Kelvin, you only have per mole 2.478 kilojoules. Need that many kilojoules per mole, have that many kilojoules per mole. EA is much greater than RT. So this is going to be a pretty slow reaction. Okay. Well, what if the activation energy is, say, 1.34 kilojoules, or make 1.32 is what I have in my notes. Okay, well then, and still 298, now 1.32 is smaller than 2.478, right? EA is less than RT. Okay, and so this reaction is going to be relatively fast. Okay, so I have a really more interesting question to end with, really. It's the last thing I'm going to talk about. And that is why, if EA is greater than RT, why do reactions happen at all? Why do reactions happen if EA is greater than RT? Okay. Why the barrier? So what's the answer to that question? Why would there be any that have the energy to go over the barrier? And the answer to that is that there will always be above average molecules and And so there'll always be collision complexes that have above average kinetic energies. Okay, so those molecules would be moving at greater speeds and they'll have the needed energy, right? There'll always be some and that will be able to go over the barrier. So you might want to know, well, how could you find out how many? How could you ever know what fraction, let's say, of collision complexes have the required energy? So how could you ever estimate the fraction with the required activation energy? Which actually tells you, we know what the, for example, we know that the root mean square speed, we know that this is the square root of 3RT over the molar mass. So we know what that is. So does this help? Does this help to get us to help with us figuring out this fraction? And the answer is no. Really, an average, you know, all we know is the root mean square speed. We know the average kinetic energy. Okay, but averages are very limited. And here's an example, you know, if you have the number 2 and the number 12, the average is 7. If you have 6, 7, and 8, the average is 7. But this set of numbers and this set of numbers are like very different. So when you know an average, you don't know much. Okay, so knowing the root mean square speed and the average kinetic energy is great, but it's not enough. Okay, in order to figure out things like the fraction of molecules that have above a certain root mean square speed, things like that, we need to know something about the speed distribution function. The speed distribution function would help us with the fraction that we've been talking about. So I'm going to talk about, I have already recorded a class from September 21, 2020. So this is continued. On the September 21, 2020 video. And I'm not sure how much I will finish at the end of Wednesday, September 22, 2021, but if I spill over, it'll be into this video that I recorded last year. Okay, so let's say goodnight and go have dinner. Thanks. Have a good day yourselves.